So let's break down the shell method. Where the shell method, you want to imagine nesting concentric cylinders. Concentric, of course, because they all are centered around the same axis of rotation. All right, so we graph the function over the given domain and range. We find and label the axis of rotation, as per usual, either with an arrow like that or an arrow like this, depending on which way we're going. We draw an approximating rectangle, as always. And for the shell method, the axis of rotation is always parallel to the radius of rotation. So keep that in mind. So for the washer and disc method, it's perpendicular, but for the shell method, it's parallel. So if you know which method you're using and which axis of rotation you have, you actually know which way the rectangle must be. So you take the thickness of your shell, which is either dx or dy, and you'll label that. And then you have your height. So if it's a vertical axis of rotation, your height will be f of x minus g of x. If it's a horizontal axis of rotation, it'll be f of y minus g of y. So it just depends. Outer minus inner. And if your vertical axis of rotation is, the radius of the vertical axis of rotation is r of x or r of y. Now let me show you what I mean down here on the picture. So we have this lovely, lovely rectangle. Our axis of rotation is this direction. So you'll notice that the rectangle is parallel to that axis of rotation. It's not perpendicular. Perpendicular is the wash method. You're not cutting across it. You're nesting inside, right? Your axis of rotation goes down the center and your rectangles are parallel to that axis of rotation. The rectangles that you sweep around to form your cylinders, your cylindrical shells. Okay, now this distance from here to here is r of x. It's your radius. The thickness of your rectangle is dx. And then this big distance, right? So you want to think about how high up this is. So from here all the way down, that's f of x, right? That curve all the way back to the x-axis is f of x. And this little curve right here is g of x. Now maybe you see what I mean when I said the height is f of x minus g of x. It's the long height from 0 up to that top part, and then from 0 up to that small part. And the difference between those two is the length of that rectangle. Right? So I can say that. So the length is f of x minus g of x. All right, so, and that's what we've written right down here. 2 pi radius, height, right? This is the height right here, or the length, times the thickness. Now, we'll talk about the axis of rotation. Give me one second. Well, actually, let me do this right now. If your axis of rotation is the y-axis, which it is in this particular example, you might have noticed that there's actually a simple answer for what r of x is. So the distance from here to that value is x. So if the axis of rotation is the y-axis, then r of x is equal to x, which actually will do a lot. So if the axis of rotation is one of your axes, then the then the radius is quite simple. The radius is x. Similarly, if it's a horizontal axis of rotation, if it's the x-axis, then we run parallel to that x-axis like this. And so then we have this distance right here, that's r of y, which if it's the if it's the x-axis, then it would just be y, right? Whatever that height is, that's y. Now, the thickness is dy. no problem. And then the distance between the two, okay, from 0 from the y-axis out to that edge is f of y. And from 0 out to this little inner edge is r of y. G of y, excuse me, G of y, because that's r of y. So G of y gets you there to there. Because you're looking at given y values. Given the y value of 2, that distance from 0 out to that edge is f of y. From 0 up to that edge is g of y. That's why it's f of y minus g of y. Right down here. Together, those give you the height of that cylinder, the length of that cylinder. And then r of y is the radius, of course, because you're swinging it around. What you're doing is a cylinder, right? And you're swinging, well, pick a smaller one. Maybe this one? Nope, too small. There we go, right? So you're swinging that little rectangle gets swung around that axis of rotation, right? So that cylinder has a radius, and then it has a length depending on what's the distance from this end to this end. Okay. Oh, and I better label that length. Let me just put that in there. So this length right here, that height, length, whichever way you want to think of it, height or length, tomato, tomato. Same thing. So that length is f of y, the outer ring, or outer edge, minus g of y. So let's put our theory into practice with an example. So we're going to have a region that's bounded by x squared plus 1, x equals 2, y equals 0, oh, and x equals 0. So I've got x squared plus 1 drawn right here. So I have that lovely curve. So this is y equals x squared plus 1. X equals 2 is a vertical line over here. So there's x equals 2. X equals 0, of course, is over here. And y equals 0 is down here. So I'm looking at this region. Okay. Not my best shading job ever, I'm sure, but that's all right. Okay, so now that I have that, I've got that drawn. Computer drawing is a beautiful thing. I want to draw a rectangle inside of it. Now, where's my axis of rotation? Because the axis of rotation is going to matter for how I'm going to draw the rectangle. So it says it's rotated about the y-axis. So that means that I'm rotating this way, along or about the y-axis, around the y-axis. Now that means that my rectangle must be, I'm drawing a very wobbly rectangle here, must be parallel to that axis of rotation. It has to be like this. It's a very wobbly rectangle, but you get the idea. Okay, so what's my thickness? My thickness is this distance. That's the x-axis, so that's dx. So thickness is in terms of x. Okay, then let's look at that radius. The radius is the distance from the axis of rotation out to that rectangle, which in this case is just x, because the axis of rotation is the y-axis. And we said when your axis of rotation is the y-axis, then your r of x is just x. So my r of x will just be x, no problem there. Then I need my height of my rectangle. The height would be equal to this distance right here, which would be from 0 up to that curve, but that's what x squared plus 1 is. I mean, that's how we define functions back in algebra class, right? It's this curve, so that height would be that curve, right? Because it's from 0 up to that. And then, sorry, my rectangle's really bothering me. I don't know why. There we go. That's a little bit better. Then all I need to know is where is my starting point and my ending point. But those are kind of easy, because if I'm going to go in terms of x, if x is my variable, then I'm going to look over here at the start. It was x equals 0, and at the end, it's x equals 2. So this is A, and this is B. All right, lovely. Okay, so the volume is equal to 2 pi integral from a to b of r of x times f of x minus g of x dx. I know it's that one because I know it's dx because of my axis of rotation being vertical. All right, so that's 2 pi times the integral from 0 to 2. R of x we said was x. F of x minus g of x is the height, which was just x squared plus 1. So that's all there is to that one. And then my thickness is dx. Right, like that. All right, then. So I can distribute. So this is 2 pi integral from 0 to 2. X times x squared is x cubed plus x. Now you'll notice it's missing all that squared bit with the foiling that we had in the disc and washer method. That's one of the ways this method can actually be a bit easier because we don't have all that squaring. I just needed to distribute my x there. So this is 2 pi, and then the integral of this would be 1/4 x to the 4th plus 1/2 x squared from 0 to 2. Sorry, 0 and 2 are in pink. The 0 won't matter because this is a polynomial, so the 0 is just going to be 0. So it'll be 2 pi and then 1/4 times 2 squared, or 2 to the 4th, sorry, 2 to the 4th plus 1/2 times 2 squared. Minus 0. The back end's not going to give anything for you. All right, so then I just need to know what this is. Let's see, 2 to the 4th is 16. 16 divided by 4 is 4. So that's 4 plus 4 divided by 2 is 2. So that's 6. So that's 12 pi. And I believe this was meters, so it's meters cubed because, of course, we're finding a volume. A decimal for this would be about 37.699 meters cubed. Oop. My m has too many humps in there. All right, m cubed. There we go. And of course I can check myself with Desmos. Nothing's going to stop me. So there we go. We can see it. There's the rectangle. There's the region. I've got it all graphed and shaded and lovely. And then the integral calculation is 37.699, which I can check that that's 12 pi. Sorry. I can check pi. I can check that that's 12 pi. So it's 37.699.